to the next seminar. So I'm delighted to introduce Karri DiPetrillo from University of Chicago. So Karri is an experienced experimental particle physicist who's worked on both ATLAS and CMS. She originally got a PhD from Harvard University before moving to a fellowship at Fermilab. And since this year, she's been assistant professor at the University of Chicago. So I decided to invite Karri because I'm very interested in these future collider opportunities, specifically Muon colliders. And Karri's been very vocal about her support for future colliders and Muon colliders. And I think, like me, many of the people in the audience are also very interested in this. So I'm excited to hear what she has to say. And Karri, I'll leave it with you. So yeah, thank you.
Thank you for that super nice introduction and for having me. Right, so I'll start telling you about sort of the path towards a 10-TeV Muon collider. And I kind of like starting with sort of the things that you hear around the coffee break during conferences where we talk about future colliders and things like this. So have heard one very famous lab director say a Muon collider will never happen in our lifetimes. Another lab director saying there are still 10 or 12 miracles needed for Muon collider. You'll often hear, oh yeah, you can solve everything but the neutrino radiation. And then I think there's also this perception that a lot of the enthusiasm was just a bunch of naive kids at SNOMAS, the US particle planning, US planning process for particle physics. And so with that in mind, I want to talk about first the physics case for a Muon collider, and acknowledge and discuss some of the technical challenges and where we are in terms of readiness. And the goal is that I want you to walk away from this talk convinced that we should begin R&D. So why do we need a new collider? What is the physics case for going to the multi-TeV or the 10-TeV scale? So generically, I think our goal as particle physicists is to understand the smallest irreducible pieces of matter, fundamental particles, and the forces that govern these particles. So going all the way from the DNA that makes us all human, to atoms, nuclei, protons. Oh, sorry. I guess that wasn't a question. Is someone's just unmuted? All the way down to the electron and quarks, which are the fundamental particles that make all of us, make up all of us. So our best known description of the fundamental particle content of the universe is the Standard Model, sort of sketched out here, with our fermions and bosons, and there are several pieces that we don't understand. So in particular, if we're thinking about the most recently discovered particle, the Higgs, there's still quite a bit that we don't know about it. The Standard Model also doesn't have an explanation for neutrino masses and why they're so small compared to everything else. I look at this sort of sketch and I wonder, is there some deeper underlying pattern? Like the periodic table of elements has a deeper underlying pattern, which points to sort of the fundamental particles that we know. So maybe there's something going on here. We also know based on observations of the universe that it's incomplete. So we're fairly convinced that dark matter is a particle, but we have no explanation for dark matter in the Standard Model. If we think about the origin and evolution of the universe, if we think about the early universe, we also have no explanation for baryogenesis. If we think about the stability of the universe, we're still not quite sure where we are there. And so the great thing about colliders is that it's a controlled experiment to directly probe the smallest scales and to probe the conditions of the early universe. And so as we've gone to higher and higher energies, this has been extremely successful. We've been able to establish and test the Standard Model, and it makes sense that if we go again to higher energies, perhaps we can break through and answer some of these questions that we've had. So where are we in terms of the high energy landscape today? We've finished run 1, run 2, and we're in the middle of run 3 of the LHC. When we turned on in run 1, we discovered the Higgs. And in run 2, we continue sort of probing the TeV scale with an energy increase. And so far, there's been no signs of beyond the standard model physics at the LHC or anywhere else, especially in some of the more obvious channels that we have. And so as we start thinking about collecting larger and larger data sets, starting with run 3 and looking forward to the high luminosity LHC, I think some of the things that are clear are that nature is more complex than we expected. The new physics isn't what we were expecting. We know that we need to fully leverage future LHC data and detector upgrades to fully explore the TeV scale. There are still a lot of places we could look and potentially find new physics. But we also know that given the LHC will end in 2040, we need to already start planning for what comes next. Future colliders take a long time to decide what to do and to build. What I think is a little bit less clear is what future colliders should we build? And I think something that's often missing from the conversation is how can we convey the necessity of future colliders to ourselves, particle physicists, other scientists, and the public. And I think focusing on what is truly unique to colliders is important, right? They are beautifully controlled experiments, and that's great. But what's really unique is that it's the only place where we can produce and characterize heavy standard model particles like the Higgs boson. Given the centrality of the Higgs to the standard model and all of the questions that we've had that we still have surrounding it, this is what makes colliders really a unique and powerful tool. So using the Higgs kind of as a framework for thinking about which future colliders to build and trying to convince people that we should build something, I think is really useful. So just thinking about some of these questions, the first one that might come to mind is it a standard model Higgs? And the way that we would answer that or start by answering that is seeing if the Higgs couples to other standard model particles as we expected. And if it doesn't, maybe there are some interesting implications for the origin of flavor, neutrino masses, or dark matter. And so we've done this, and this is a really nasty plot from CMS, but it's super rich with information. So this is sort of, you can think about Higgs couplings to other particles, if I'm focusing on the W here. And you can see sort of the uncertainties on these couplings as you go from the discovery data set to the full run 1 data set to full run 2 and projections for the high luminosity LHC. And so you can see that we're already sort of approaching precisions of a few percent, and by the HLHC we'll definitely be there. And if you think about what kind of scales this is indirectly probing, it gets you to sort of the TeV scale. So we're actually probing energies that we can directly search for new particles at the LHC. Okay, so then the other thing that we want to understand is what is the microscopic nature of the Higgs? So far, it's the only seemingly fundamental spin zero boson. We know that means it's highly sensitive to quantum fluctuations, right? So if you try and compute the Higgs mass, you get these terms that blow up depending on what your cutoff scale is. And so the question is there new physics that's preventing the Higgs mass from being pulled all the way up from 125 GeV to the Planck scale? And so there are a few sort of really well-motivated potential explanations for this, including a new symmetry, which would sort of protect the Higgs mass and provide some nice cancellations, and result in many additional particles like supersymmetry. Or is the Higgs composite like the pi? Given sort of LHC results, we expected some of these new particles that would be predicted to show up. And so either it means that the potential solution to this problem isn't what we expected, or these new particles are sitting just above the TeV scale. We can also kind of think about other ways to sort of make a guess at where new physics might be showing up. And I think it's really interesting that both sort of the top-down and bottom-up approaches for trying to make guesses of where to look next, both require going to the 10 TeV scale or higher. And so what I mean for that is if supersymmetry is the thing that is protecting our Higgs mass, if that's the new physics, the observed Higgs mass actually sets direct targets for supersymmetry. You can figure out what your top partner mass would be given the mass of the Higgs. And it's pointing very much to the multi-TeV scale. From a sort of more bottom-up approach, if you think about what we observe out there in the universe, thermal WIMPs are the most simple and likely explanation for what is dark matter. But if you think about those thermal WIMP candidates and what masses and couplings you would expect them to have, we actually haven't even probed them yet with direct detection. And they're also out of LHC and HLHC reach. So you can see sort of where on a mass and a cross-section plot, you would see a WINO and a Higgsino. And the WINO maybe is in reach of next generation direct detection, but it's out of reach of current experiments. And the Higgsino is well under the neutrino fog. And so this is something where having a collider would be really uniquely suited to look for this. And these both require multi-TeV scale colliders. And then we have this other question of we've measured the Higgs mass. We know sort of the location of the minimum of the Higgs potential, but we know nothing about the shape of the Higgs potential at all. And the way that we do this is by measuring the Higgs self-coupling. And the reason that we want to do this is because knowing the exact shape of this coupling is really important for understanding these questions about the origin and stability of the universe. So if the Higgs potential looks differently than what we would expect from the standard model, maybe that points to a first order phase transition, which could explain baryogenesis. And so measuring out the shape of this potential to the level that you need to answer these kinds of questions requires measuring this Higgs self-coupling with a few percent uncertainty. And so you can see where we are currently with the LHC and where we will be with the HLHC. And the only way to get that sort of few percent precision requires producing a lot of multi-Higgs events. And this is only possible at a 10 TeV scale collider. Okay, so I hope that I convinced you that we should aim for 10 TeV at a minimum. The next question is, what should we build? And this is where I want to convince you why a Muon Collider would be sort of an extremely promising path to the energy scale. So our traditional paradigm is that we use our favorite readily available particles, like electrons and protons. They're stable, they're all around us, easy to accelerate and collide. With electrons, it's really nice that they're fundamental particles, which gives us clean collisions that we associate with precision colliders. The challenge there is that their small mass results in a lot of synchrotron radiation, and this sort of prevents you from getting sort of above about a TeV or so, at least in terms of the future colliders that we're talking about. So can't quite get you to where you want to be. We traditionally associate protons with higher energy colliders because there's less synchrotron radiation. The trade-off is that they're composite particles. So you're colliding the quarks and the gluons, which carry a fraction of the proton momentum. And there's also a large rate of messy sort of low momentum background in all of your collisions. And so we have this dichotomy of precision versus energy. And going to higher energies, the traditional paradigm has been to sort of take a fixed technology and think about going bigger. Or then improving the technology and still going a little bit bigger. So if you think about the energy of a beam that you can achieve with a dipole magnet and a certain collider size ring, you can sort of make projections for how big the next proton collider needs to be. So for the niobium titanium magnets that are in the LHC currently, you need to be close to 200 kilometer circumference. For niobium tin magnets, this is sort of like record strength optimistic still. You need to be at 100 kilometers. And then for future high temperature superconductors that we have no idea how to make, you need to be at 80 kilometers at a minimum. And so this is sort of what CERN is aiming for in terms of having a future circular collider. But at a certain point, you have to wonder how much larger can we go? Actually, digging 100-kilometer tunnel is extremely challenging, especially in one of the most expensive areas on Earth. And so then you need to think about, can we take a risk on new technology? And so the Livingston plots that we're sort of used to seeing can be broken down into different accelerator and then collider technologies. And we can see that real energy breakthroughs require leaps in technology and fundamentally new concepts. And so even with those sort of next generation magnets, we're pushing the limits of what is feasible in terms of tunnel length. And we're also pushing the limits of what's feasible in terms of power consumption, because it doesn't just scale with sort of this mass term, it also scales with the number of protons or particles that you need in your beam. So it gets extremely expensive. And this is where the muon comes in. And they break this paradigm of larger and larger E plus E minus and PP machines, because you're colliding fundamental particles which have more mass than the electron, effectively no synchrotron radiation. So in terms of the footprint of your collider, it's really nice. You could have a 10 TeV collider that fits within the Fermilab site. It's nice that you don't have to go off site to dig a tunnel. It could also be situated at CERN without having to dig much in the way of new tunnels. And you can see it's much smaller than sort of any of the other higher energy machines that are sort of out there. And what's really nice is that the luminosity per like wall plug or power improves as you go to higher energies. So everything gets easier as you go to higher energies because the lifetime is boosted. It's also more than just a lepton collider. So as you go to higher energies, your muons start to radiate W and Z bosons, and you actually get electroweak precision physics in the same machine. So you have the energy reach from Drell-Yan production and the precision electroweak physics from vector boson scattering. And this is great if some of the most important questions that we want to answer have to do with electroweak symmetry breaking. Muons are also they create the perfect neutrino beam, because you know the exact content in terms of the types of neutrinos you have in your beam, and you also precisely know the energy spectra and intensity. And this is in comparison to neutrino beams produced by protons on target, where you also have a mix of pions and kaons decaying, and it's quite messy. And so for lower energy muon beams, this is great for doing precision cross sections, sterile neutrino searches, certain parameters of the sort of PMNS matrix are really uniquely measured in this scenario, and you can over constrain the sort of three flavor paradigm. When you have neutrinos from a high energy muon beam, we're actually not fully prepared to say how much interesting physics you can do. And I think this is kind of a new area for theorists to be thinking about. But what is nice is for people who are interested in neutrino physics, this could be a really appealing future after Dune and Hyper-K. So all this is wonderful and perfect, but what are the real world constraints? And here, the particle physicists need to defer to accelerator experts. And so during the SOMAS process, we had this implementation task force, which was tasked with sort of evaluating the physics reach based on realistic energy and luminosity that could be achieved, and projecting to get some idea of the achievable science. They were also tasked at looking at the size, the technical complexity, and environmental impact, ranking risks and making estimates of technical readiness, as well as making cost estimates from a couple of different approaches. And so the verdict was that E plus E minus 6 factories are nearly shovel ready. So I have some of the proposed colliders that we were discussing at SNOMES listed here, the energy being considered, the tunnel length, the power consumption, the projected costs, and time to start. And so you can see there are kind of three categories. These sort of E plus E minus 240 GeV colliders are, ILC, we say shovel ready, and other options maybe need a little bit more design, but are pretty much shovel ready as well. Then there's the sort of 3 TeV scale lepton colliders, which need a bit more time. And I think people were less excited about in terms of the physics. And then in terms of the 10 TeV scale that we were super excited about, the takeaway was really that we don't have the technology today for either a 10 TeV Muon collider or a 100 TeV proton collider. And we're also not ready to make any decisions. But the implementation task force did make a very strong call to begin R&D for these 10 TeV potential options as soon as possible. And there was also a sort of priority placed on R&D that aims to reduce the costs and the energy consumption of future collider projects. And so with this accelerator physics input came the sort of vision for the energy frontier from the US SNOMAS process. I think the thing that was the most surprising, even for people in the energy frontier who were participating in SNOMAS, was there was a big call for there was a lot of excitement around the idea of having a collider in the US while maintaining international collaborations, in particular at CERN. Like, wouldn't it be great if we had 2 colliders in the world and we were competing with each other and bringing out the best, and the best in terms of science. And then in terms of sort of other conclusions, it was very similar to the European strategy report. I think there was one subtlety, which was rather than an E+E-6 factory followed by a multi-TeV collider, the energy frontier really called for an E+E-6 factory and a 10 TeV scale collider. It's just that the feasibility and readiness for the multi-TeV would take longer. There was a lot more momentum for a 10 TeV Muon collider than was expected. And I also think if I had to characterize people in the energy frontier, there was a sense of urgency in terms of moving forward with R&D. There was a high priority placed on compact and power efficient option. And there was a lot of early career enthusiasm for future collider options. And so I think a lot of people who were not at SNOMAS were really surprised by some of these outcomes. In particular, why was there so much enthusiasm for Muon Collider now? You can see sort of some screenshots of the Muon Collider forum report. We wore t-shirts to sort of get people talking about the physics and why we were so excited, wrote letters, there's a Twitter, and the International Muon Collider collaboration formed sort of around the same time as SNOMAS was happening. And I think if we can look at the literature and kind of get an idea of what has happened and why the enthusiasm is so strong right now. So this is number of papers as a function of time, separated by the kind of paper. And so if you look back to the sort of 2000s-ish, you see a lot of papers associated with this initial Muon Collider neutrino factory collaboration. It dips down, and then there's a peak from the US Muon Accelerator program, but all of the papers are accelerator papers. There's no physics. And the thought is that these 2 scenarios really focused on a Higgs factory, which is extremely challenging and hard to do. It's hard to compete in particular with a 240 GeV +E- option. And so that made it kind of less attractive in terms of trying to overcome those challenges. What's changed since sort of 2012, 2014 is that there's a growing case for 10 TeV since the Higgs discovery and since we haven't found anything else. And in terms of the technical readiness for overcoming some of the challenges associated with the Muon Collider, the timescales actually look quite favorable. So all of this has combined kind of into the perfect moment, which I think there was really broad consensus that the time was right to begin in earnest Muon Collider R&D. Okay, so then I'll talk about collider challenges and opportunities. So the The challenge has to do with everything has to do with the muon's lifetime. So you need to produce, cool, accelerate, and then collide muons before they decay. And this is roughly the idea of how we would do this. We would have a multi-megawatt proton source on target, which would produce pions that then decay to muons. We would have a high field solenoid for muon capture. This would be followed by 6D ionization cooling, where the 6D means sort of three spatial dimensions and 3 momentum dimensions. And then we would need to accelerate to the sort of energy we want to collide the beams. And then we would actually need to collide, make collisions inside our detectors. So all of this is, each of these steps is challenging, and you want to make sure that you can overcome them and make the luminosity that you need to do science. So if our goal is to measure the di-Higgs cross-section, which is about a few femtobarn with a few percent luminosity and a few percent uncertainty, and other electroweak processes have similar cross-sections, this means we need about 10 inverse attobarn. Optimistically, we would assume 5 years of runtime with 30% efficiency, and you can translate this to the instantaneous luminosity that you need, and then you can translate this to the beam parameters that you want. So because we're muon limited, you would set the number of bunches per beam to 1 and maximize the number of muons per bunch. You need roughly 10 to the 12. You minimize the beam size. So in terms of what was expected from some of the early designs for cooling, you would aim for order 10 micron beam size. And you minimize the circumference of your collider ring so that you have as many muon collisions as you can before they decay. And this is set by your dipole magnets, and you re-inject sort of when most of your beam has decayed. So you need your proton source to have a rate of about 10 hertz. And you can also make projections for how many muons you're going to lose throughout the process, about 2 orders of magnitude in terms of going from protons to muons. And this tells you everything that you need to know about the proton source. So you need to deliver about 10 to the 14 protons with an energy of 5 to 8 GeV. So this is where you would maximize muon production at a rate of 10 hertz. And this translates to a proton source of about 1 or 2 megawatts. You need to make really short bunch pulses. And this creates a lot of challenges for your target, having something that can withstand such a high power proton source. But there's been a lot of progress. If you think about spallation neutron sources, at a few places in the world, we're expecting few megawatt proton sources to come online quite soon. And you also need a 20 Tesla capture solenoid, which is also synergistic with some of the charged lepton flavor violation experiments, which use muons. And the nice thing from a US perspective about the proton source is that it would really naturally build on Fermilab proton complex in terms of what's existing and what's planned and proposed for Dune. So then you have a beam sort of with like large spatial and momentum spread, and you need to cool it, you need to make it smaller. And the only way to do this in a short amount of time is to actually use DDX. So you progressively reduce the transverse momentum by passing your beam through low density absorber. Needs to be low density so that you don't make the beam spread more from multiple scattering. And then you restore the longitudinal momentum with RF cavities. And so this is what a lot of people say is the most challenging aspect of the Muon Collider. But the US Muon Collider Accelerator program from about 10 years ago actually did an end-to-end cooling design and simulation where they got to within a factor of 2 in terms of what you need for the luminosity. The mice experiment in the UK demonstrated cooling single muons as opposed to bunches in 4 of 6 dimensions. So technical progress in terms of demonstrating that this can be done with existing technology. Muon G-2 actually demonstrated longitudinal ionization cooling. And various components of this have been tested at Fermilab, and test stands are being planned around the world. And IMCC within a single year has already made a lot of progress in terms of what can be expected and done in terms of cooling. So then you have your accelerator and your collider rings. So you have an accelerator ring because you need to be ramping up your dipoles very quickly as you're injecting bunches, and then they'll decay. So you need these magnets to be normal conducting, which means their max field is typically less than you would get from superconducting dipoles. And the challenge is achieving the maximum field that you need, but also not consuming an insane amount of power from ramping up and down so rapidly. You need to be able to transfer that power somewhere and restore it. And then for the collider ring, as I said before, you're circulating 2 bunches and refilling when depleted. To minimize size, you sort of take the optimistic in terms of maximum dipoles produced in the world. And this gets you to about a 10-kilometer ring where you get about 2,000 turns per bunch. And you need large aperture magnets because your muons are constantly decaying in the beam, and you want to prevent quenches of your superconducting magnets. Then to talk about the neutrino flux, what happens is muons decay to electrons and neutrinos. And the issue is not so much the TeV neutrinos, it's the TeV neutrinos interacting with matter in between the beam and you. And what's kind of interesting is that as the beam is decaying, these neutrinos are collimated, and the width scales inversely proportional with the energy. And so what you can do is you can place the collider at a depth of about 200 meters, minimize field-free regions, and then you're kind of spreading, you're not letting this sort of spot of neutrinos accumulate in any one region. And something else you can think about doing is doing beam wobbling, either with magnetic field or high precision movers. And this gives you a sense of how much reduction you get in the neutrino flux. And then just to sort of give you projections, so if you were to take a 4 TeV Muon Collider and just look at the dose equivalent without any mitigation, you would need to place this sort of 4 TeV Muon Collider at a depth of about 250 meters to be within Fermilab offsite limits. If you wobble the beam just a little bit, you can get to an equivalent depth of 20 meters. And our goal is to be well below any sort of site limitations in terms of radiation. And it's looking like placing the Muon Collider at a depth of 200 meters and wobbling the beam gets you there and does better than you need to. And so just to summarize where we are in terms of the accelerator challenges, I think there's still a little bit of perception that there's been no progress in the past 50 years since it was first mentioned in the literature. But if you look at the past decade, you see that in terms of the superconducting solenoids that you need, putting normal conducting RF cavities in magnetic fields for cooling, demonstrating 4D ionization cooling, having multi-megawatt proton sources, fast ramping magnets, designs for the collider and the detector. All of this has happened recently in the last decade or so, and is well timed in terms of the physics needs that we have. So then to talk about extracting physics, the collision environment is messy. So your muons are decaying and producing high energy electrons, which are showering within the accelerator lattice and within the machine detector interface. And so if you think about it, you just need to worry about decays within 20 meters or so of the interaction point. This is about 10 to the 7, and the total energy of the decay products. And in order to deal with this, we have these tungsten nozzles, which helps take these sort of TeV scale neutrinos and TeV scale electrons and showers and prevents a lot of those particles that are produced from entering into the detector environment. And so we have basically a general purpose detector, silicon tracker, high granularity calorimeter, high field solenoid and muon detector with these nozzles in the forward region. And this was something that was a major outcome from SNOMAS and the recently formed IMCC. And so this kind of explains and shows you what the nozzle does in terms of background. So this is supposed to be a single muon decay. And you can see it's decaying from this side. You're mostly in the nozzle and the accelerator lattice producing a lot of neutrons, which are mostly captured and don't enter into the detector region unless they're extremely low energy. And so you can see the change in the particle content if there is no nozzle in black for electrons, photons, and neutrons, and if there is a nozzle in red. And it does better overall to have it. So in terms of the detector environment, it's similar dose and fluence to the high luminosity LHC, which is great because then we know we can handle that. And if you want a point of reference, 100 TeV proton-proton collider is about 3 orders of magnitude worse. And if you want to think about the properties of the background in the detector, so with the tungsten nozzle that has been assumed, you have about 10 to the 8 very low momentum particles per event, but it looks extremely different from signal. The majority of these particles are less than 200 MeV. They have really unusual pointing and direction. They're coming in from the sides instead of from the collision point, and they're partially out of time. And the details can change depending on the beam energy and lattice and various things, but overall, that's the picture. In terms of occupancies, a little bit higher than the HLHC, especially for the innermost layers of the tracker. This is the most challenging part of the detector by far. So you design your tracker optimizing for less than 1% occupancy, and you take techniques that we have from the high luminosity LHC upgrades to mitigate your hit rate. So if you start, you have about 1,000 hits per centimeter squared per event. This is meant to be in gray here. And if you only select hits in a 3 sigma time window, assuming 30 picosecond timing resolution, you get more than an order of magnitude reduction in your hit rate. And then something else that we can do is like the CMS doublet layers in their strip tracker that they're planning. We can do the same in our pixel detector and look for coincidences that point back to the interaction point. And this gives you another factor of rejection as well and gets you to where you need to be. It does mean that it's kind of the ultimate tracker. It's about 100 meters squared of silicon sensors, 2 billion channels, but there are a lot of promising R&D directions in terms of the sensors. Monolithic sensors, devices with intrinsic gain, get you to a 30 picosecond timing resolution, which will be used for the HLHC. You probably also want intelligent pixel sensors where you can get data reduction on chip, which would be very useful for overcoming challenges with power consumption, data acquisition, and trigger. But again, this with some reasonable extrapolations to where you would be, it looks feasible. In terms of the calorimeter, you can see this is what a signal photon would be from the collision compared to beam-induced background. But again, this is largely out of time, extremely low energy cloud of neutrons. And so with a fairly simple design in terms of ECAL and HCAL, timing resolution of about 100 picoseconds and longitudinal segmentation, you can do pretty well. You have efficiencies and energy resolution sort of similar to the LHC, and there's a lot of room for improvement, especially if you improve your calorimeter design and implement smarter reconstruction techniques. This was really a first brush. And then you need to do reconstruction, and so far it works well, but it is definitely an active area of development. You have about 100 fake tracks per event after making some basic PT number of hits and quality of fit requirements. But even still, you can see sort of your this is your photon energy resolution and your beachhead momentum resolution, similar to that of a hadron collider. And what was wonderful was seeing that you can extract high quality physics in the face of fully simulated beam-induced background. And for the most part, you had pretty good agreement between fast and full sim, because your particles produced in the collision are so obviously different from that of the beam-induced background. And you can see that the projections for the Higgs self-coupling, searches for new particles in composite Higgs scenarios, even challenging signatures like disappearing track, the Muon Collider is reaching targets that we decided are sort of important for reaching the 10 TeV scale. So where are we since Snowmass? So Snowmass was more than a year ago. We've had the second International Muon Collider collaboration meeting, which was fantastic to see all of the progress that was made in just 1 year, going beyond the Muon Accelerator program designs of the 2010s. There's a Muon Collider demonstrator project, which was funded by the EU and includes a design study for the collider complex at 10 TeV, bringing in about 7 million euro. There is also a US effort, which is giving input in an ask to P5. So if Snowmass is the academic exercise of what is the science we want to do, P5 deals with the budget realities and prioritizes projects. And in the past year, there's been a lot of excitement for major meetings dedicated to Muon Colliders. So for the US specifically, a proposed Muon Collider R&D program was presented to P5, which incorporates an accelerator ask and a detector ask. And the report is supposed to come out in December, so we'll know more soon. But in terms of what the future could look like, optimistically, we could be on our way to prototypes, a demonstrator, and designing a Muon Collider front end somewhere in the world within this decade. And as a US person who would love for this to happen at nearby Fermilab, we can be setting the stage for potential Muon Collider to follow Dune. And this is an ambition that is shared by the leadership of Fermilab, which is quite exciting. And so to conclude, a multi-TeV Muon Collider would be a paradigm shift for the energy frontier. It's a fantastic place for particle physicists to contribute. And the ask is pretty modest. It's just for R&D this decade, so that we can put ourselves in a position to decide what to do in the next decade. And to be there, we need to start now. And so I know some of you guys said you were already very excited, but if you're just hearing this talk and you're not really sure what to make of it, decide for yourself and get involved. And I have some resources. In particular, this Collider Implementation Task Force is a fantastic resource for getting started in terms of figuring out how you feel about future colliders. All right, and that's it. Thank you very much.
Thank you very much for a great talk. Yeah, do we have any questions? Please just go ahead and unmute yourself. Bruce?
Hi, thank you for the talk, which is excellent. I have a question about those tapered tungsten blocks that you mentioned at the end point. What did you call them? Nozzles or something?
Yeah.
Yeah. So, I mean, I'm just trying to get my head around this because the background conditions here are sort of qualitatively different to what we're used to. So, so these are tungsten because you are trying to exhaust or range out the electromagnetic showers from the produced decay electrons. That's the point?
Yeah, yes. So the majority of it is tungsten because you're trying to stop the high energy electron from entering into your detector region and also stop all the subsequent particles in the shower.
Yep.
The trade-off is that you do produce a lot of neutrons, and so people are sort of seeing what happens if you coat the nozzle in something that would help reduce those neutrons.
Yeah. So you've got the nozzle coated with a boron-rich with something boron rich in order to get the low energy neutrons. So the neutrons are coming from what? They're coming from showers from the small amount of the very high neutrino flux that interacts with things, or they're coming from,
I think the electron showers.
Say again?
The electron showers. So just like the calorimeters in our main detector area have a neutron cavern background that they produce. It's kind of the same idea. So trying to reduce the neutron tungsten background.
Yes, sorry, there's something I'm missing. You're not getting neutrons directly from muons or from electron-initiated showers. So where are they coming from?
It's from interactions in the tungsten.
Interactions of
of the shower particles from.
Okay, so there are so many shower particles that it's the small fraction of those shower particles that undergo some sort of nuclear interaction that sets out a neutron. Okay. I mean, that fraction must be small, but then the number of particles generated in the shower is very large. Okay, I think now I understand. But again, that must also mean that the neutrons are disproportionately at very low energies.
Yes, and you can see sort of the energy distribution for neutrons if there is no tunnel in gray, and if there no nozzle in gray, and if there is in red, and it is extremely low energy.
Okay, so you expect the boron to be effective
the
provided that it's deployed in the right, geometrically in the right place. Okay, I think I understand that. Thank you.
Can I ask? Great talk, Karri. I was trying to figure this out, and I guess you touched on it, but is there a reason why the LHC tunnel can't be used for Muon Collider, or has that been pursued? I guess it's too big. Is that the problem?
So for 10TeV, it wouldn't make a great collider ring, but it would make a great accelerator ring. And so the IMCC's design, they have a 27-kilometer circumference accelerator ring. So I think that's kind of what they're anticipating. And then the idea would be that you do need to dig a collider tunnel, but it would be smaller than the LHC.
Right, got it. So that collider tunnel, I think that's what I was piecing together. That would be the 10-kilometer tunnel, instead of a 100-kilometer tunnel.
Instead of 100, yeah.
Right. Okay.
So this is sort of I think this is 16 kilometers circumference in the Fermilab scenario, and then 27 in the IMCC, and the collider ring is about the same for both.
Okay, great. Thank you.
Mikhail?
Yeah, thanks. Thanks for the nice talk, Karri. So recently there was a proposal for mu plus collider. So some Japanese groups suggested that. And I think the reasoning was that the technology is much more advanced for antimuons than for muons to cool them, kind of from those muon experiments. Do you think that's something feasible, or can you comment on that? I'm just curious. To hear from an experimentalist who's working on a Muon Collider instead from theorists who have been proposing.
Yeah, so the thing that I really like about mu plus mu minus is the sort of the Drell-Yan production and the vector boson fusion, whereas if it's just mu plus, I'm assuming they're talking mostly about the vector boson fusion production.
Yes, that's mostly, yeah.
Yeah, so from an energy reach perspective, I would really push for the mu plus mu minus, because you get the Drell-Yan too, you get the energy reach. I have to apologize, I don't know enough about the cooling for anti-muons versus muons and how difficult that is to say whether this kind of proposal makes more sense.
Yeah, I guess for anti-muons you can just produce muonium, and then you split the muonium and get your cool muons, anti-muons from there. So that's used for the G-2 experiment.
I see. Okay.
In Japan at J-Park.
Okay. Interesting. All right. I would need to think more about that. But it's an interesting proposal for sure.
Yeah, good. Thanks. Yeah.
So a bit of time for maybe a couple more questions. Anyone want to go? Maybe I will then in that case. Just a general question, if you have any more comments about the environmental impact and at what level that is being considered.
I think
in terms
people
of
are
power
taking.
consumption, but also the developing infrastructure and stuff. Is it sort of enough? I mean, is it simply just a question of power, or is it just the general? I mean, how much investment we want to be making into these huge infrastructure projects? I mean, to what extent does the US political climate is this enough of a hot potato that you have to consider this quite carefully, or is it just going to be if there's enough willpower, it will get done?
That's a very good question. So okay, I think there are a lot of things going on in this space. So I think people are taking the climate impact of future colliders extremely seriously. So the FCC started out with a really interesting climate study that they did evaluating sort of carbon footprint of operating power consumption, but also looking into the impact of digging the tunnel. And in terms of digging the tunnel and all of the concrete that you need to make the tunnel, it actually seems like in most cases, the larger the collider you have, that winds up being the largest impact, especially as our power sources rely more heavily on renewables or nuclear power. For instance, in Illinois, most of the power is actually nuclear power. So relatively clean compared to the rest of the US. So I think people are taking this very seriously. There's a linear collider proposal from a group at SLAC, and they put out another paper looking in pretty good detail as well. And I know for a fact that CLIC and the IMCC are doing very serious studies as well. In terms of the political climate for a large-scale science project, I think the political climate in the US is in an interesting place, and I won't comment anymore on that. But I think that the science case, if we can communicate it effectively to Congress and to the public, I think there's enough enthusiasm that we have a good shot. Certainly, we have a good shot at R&D, and then we see where we are from there. Yeah,
Bruce, did you have a comment?
Yeah, sorry, it's another thread. If you're happy with the answer to that question, so you mentioned these sort of beam wiggling options to mitigate the backgrounds in the environment of the ring. Let me ask the opposite question. In some other muon storage ring or collider-based designs in the past, there have been deliberate straight sections that then double as an extraordinarily bright neutrino beam, or a second detector for a sort of a parasitic program in neutrino physics. Now, you didn't mention anything about that, but people must have thought about this in the process. So can you comment on the prospects for a secondary program in neutrinos?
Yes. So I think in the US, at least during SNOMES, the neutrino community was extremely focused on DUNE and their proposed DUNE phase 2. The neutrino theory community was very excited about the prospect of neutrino factories becoming in favor again. And so for other people, as you said, the way that you get this perfect neutrino beam is you have the straight sections, and you're pointing this cone sort of in the same direction at your detector of interest. For the neutrino factory, historically, people have talked about sort of lower energy beams. So that way you can do oscillation measurements. Because if it's like TeV neutrinos, you're not observing the oscillations that you want to observe. And so because it's a lower energy muon beam and lower energy neutrinos, the cross-section is a lot less of a problem in terms of radiation hazard. The radiation hazard increases as you go to higher energies because the cross-section of your neutrino beam is increasing and because the size of this cone is decreasing. So you're focusing everything into one smaller place.
But then at the same time, that's producing an extraordinarily bright neutrino
beam.
And it seems, I mean,
crazy not to use it.
Crazy not to use it. I mean, I mean, straight sections come by themselves, okay? I mean, anything that's not actually in a dipole is a straight section. So, I mean, we talk about it being a ring. Of course, we know it's nothing of the sort. So, I mean, one can imagine something as simple as you have a slightly longer straight section than usual. You make sure that it's pointed slightly downward, and you have a secondary cavern somewhere.
Yeah, so I think that there is interest in doing this for sure. The question of where you want to put that where you want to point that straight section and which part of the collider ring you want to take it from, I don't know that that's been answered yet. I know that the map community, they've talked about just sticking a neutrino detector sort of where your collider detector,
sure,
because that's a straight section,
as has been done
and
for
having
the
that point
LHC
somewhere.
Yeah,
as has been done for the LHC, exactly. Yeah, but there might be other straight sections that would be more favorable, and that I'm less sure about.
Thank you.
Okay, so we're at the hour. So if anyone has any final questions, please go ahead. But if not, we can let Karri go. Actually, I did want this might bother me. This stuff I'm really not familiar with at all. But I mean, I got from the sort of context of your discussion that this is basically like a Fermi-like restriction on the dosage of radiation that people would receive on the surface. And is that I don't know. I don't have any feel for that number. So is that like a bad? Is that unhealthy? Like that dosage, or is this just being cautious?
That's a very good question. Yeah. So this is integrated over a year, right? So if you stand in this spot where the beam is coming out for even several hours, you're fine, right? Just to make that 100% clear.
Yeah.
And this less than 100 microsievert per year, this is a factor of 10 higher than CERN's offsite limits. But if you think about like the typical flight, you're receiving about 3 microsievert per hour, right? So this, if our goal is to be less than 10 microsievert per year, we're doing pretty good.
Yeah. Okay. Thank you. So yeah, thank you again for that great talk. I will just stop the recording.